Welcome to the Explainer. Today, we're going to crack open a powerful mathematical shortcut that turns terrifying differential equations into, well, simple algebra. This technique is an absolute game changer in fields like engineering and physics, and we're about to show you exactly how it all works. All right, so here's our game plan. First up, we'll introduce you to the calculus nightmare. Then we'll reveal the Laplace shortcut. After that, we'll get into the real secret sauce, the power of shifting, learn how to decode the answer, and finally, we'll put it all together to conquer that problem.
Okay, first things first. Let's meet the beast we're going to tame today.
So take a look at this thing. It's a second-order initial value problem. Now, if you've ever wrestled with one of these using the old-school methods, you know it can be a real headache. You'd have to find the homogeneous solution, then track down a particular solution. It's just a marathon of steps.
I mean, come on, there has to be a better way, right? A shortcut to avoid all that heavy lifting. And, well, there is. What if we could just translate this entire problem into a different mathematical language, one where the solution is just a few simple steps away?
Okay, so this is where things get really cool. Let me introduce you to our secret weapon, the Laplace transform. The core idea here is just brilliant. We take our problem from its home in the time domain, the t domain, and we transport it into the s domain. In this new world, our messy calculus problem magically becomes a simple algebra problem. We solve it over there where it's easy, and then we just translate it back. It's like a mathematical round trip. Now, to really make this work, we need a special tool in our toolkit. And this is the big one, the first translation theorem. It's specifically designed to handle that pesky e to the 3t part without breaking a sweat. Seriously, this theorem is amazing. It basically says that if you already know the Laplace transform of some function, multiplying that function by an exponential is the same as just doing a simple shift on its transform. It's an unbelievably elegant shortcut. And here's the best part. It boils down to this super simple two-step process. First, you just pretend that exponential part isn't even there and find the transform of whatever's left. Then, you just go back to your answer, and everywhere you see an s, you swap it out for s minus a. That's literally it. Okay, let's see this in action, because it's almost too easy. Say we want the transform of e to the 5t times t cubed. All right, first we look up the transform of just t cubed. You can find this in any standard table. No big deal. It's 6 over s to the 4th. Now, because of that e to the 5t we had, we just replace that s with s minus 5. Boom, done. No crazy integration, nothing. Okay, so we've jumped into the s domain, we've solved our algebra problem, but we're not home yet, right? We've got this answer, but it's in a different language. We've got to bring it back to the real world, back to the time domain. So, how do we do that? Well, luckily, this is a two-way street. The rule works in reverse. If you're looking at your solution in the s domain and you see a term like s minus a sitting there, that's a huge clue. It's basically screaming at you that your final answer is going to have an e to the at term in it. It's a total giveaway. Now, I'll be honest, the answers you get in the s domain can look, well, a little intimidating at first. But don't you worry, we've got a couple of classic algebra tools to whip them into shape: partial fraction decomposition and completing the square. So think of this slide as your handy little guide for partial fraction decomposition. It shows you exactly how to take a big, messy fraction and break it down into these nice, simple, bite-sized pieces that are way easier to handle. But what happens if you get a quadratic in the denominator that just won't factor? You know, one of those stubborn ones? Well, that's when we pull out our other tool, completing the square. What this does is it kind of reshapes the whole expression, and in doing so, it reveals a hidden shift, something like s plus 2 squared. And wouldn't you know it, that new form is a perfect match for our inverse shifting rule. This is how we deal with things that turn into sines and cosines. All right, the training is over. We've got our transform, we've got our shifting theorem, we've got our algebra tools. It's time. Let's go back to that calculus nightmare from the beginning and take it down step by step. Step 1, we take the Laplace transform of the entire equation, both sides. And here's the really neat part. The rules for transforming derivatives automatically take care of the y double prime and y prime. They turn them into algebraic stuff involving y of s, that's the transform solution we're looking for, and they plug in our initial conditions for us, all in one go. And right here, this is the magic of the whole method. Just like that, the differential equation is gone. Poof! What we have left is a pretty straightforward algebra problem. All we have to do now is just move some things around and solve for y of s.
All that calculus got bundled up into that one single transformation step.
So now we've got our answer, but it's still in the S domain. To get it ready for the trip back home, we use our partial fraction skills on that first term. This lets us break down the whole y of s expression into 3 separate, much simpler little fractions that we can actually recognize from our transform tables.
And here we go. This is the final step on this side. We just take each of those simple pieces and invert them one by one. And look, every single term has that -3 shift in it, right? So we know every single term, and our final answer is going to have an e to the 3t attached to it. It's that predictable.
And after all that, there it is, the clean, beautiful solution to what looked like an impossible problem. All thanks to this amazing journey through the S domain. Okay, so let's do a quick recap of the big ideas here. The main thing to remember is that Laplace transforms give us this structured, almost recipe-like way to turn gnarly calculus problems into algebra. The shifting theorem is our go-to shortcut for anything with an exponential, and our trusty algebra tools are what get us back home. So we've just walked you through this incredibly powerful technique, a new way of looking at differential equations. We've handed you the shortcut. The only question left is, what problems are you going to solve with it?